Day 71, the theory of plate tectonics. Before we get to that though, let's review what we learned yesterday. Here is a illustration of the interior structure of the Earth. It's not exactly the same thing as what we have on your review sheet, but I want you to look at this and then transfer the information as needed to the other page. As you listen carefully to this little discussion, I will answer all the 10 questions on the first review section of your packet for today. The outside of the Earth is known as the crust. It is made out of solid rock of many different kinds, mostly granite, but also marble and limestone and other types of rock as well. But it's solid and brittle. It's only about 10 miles thick on the average. And then we have the mantle that is underneath. The mantle is made out of flexible rock, and it is the majority of the Earth. About 80% of Earth is the mantle. It is like Play-Doh, sort of, or silly putty, where it's solid, it holds its shape, but when you push on it, it can change its shape and flow in certain ways. And then below that we have the outer core. The outer core, we believe, is liquid iron and nickel. We can tell that it's liquid because of the way earthquake waves go through it. Below that we have the inner core, and this is solid iron, they believe. Nobody's been down there, of course, and so we can't tell for sure, but that is our best guess. Underneath the ocean, the crust is going to be thinner than underneath continents, and it's made out of slightly different kinds of rock. The crust here is made out of basalt, and we call that oceanic crust. The crust that's underneath the continents is going to be much thicker than under the ocean, and we call this continental crust. Continental crust is made mostly of granite, but of course many other kinds of rocks as well that we see around on the dirt. When we combine the two kinds of crusts, oceanic crust and continental crust, along with the top part of the mantle, we combine those three things to be called the lithosphere. And I will write that here. The lithosphere is the continental crust, the oceanic crust, and the top part of the mantle. The reason why the mantle is so flexible is because of the high heat that's there, the high temperature. And because it has this flexibility, it can flow. Hot mantle comes off of the inner core, outer core I should say, and rises, and it cools, and the cold mantle sinks. And this circular pattern here of rising hot mantle, sinking cold mantle is called a convection current. The crust is not one giant piece of rock. It comes in sections. Some of these sections are as large as continents, and we call each one of these sections a plate. I'll write that down over here. Just like a dinner plate in terms of the spelling. Okay, with that little discussion, you should have gotten all the answers for the first page of your handout today. Rewind if you missed something. Let's go on with your notes. Once again, the lithosphere is the combination of continental crust and oceanic crust and the solid upper part of the mantle. That is the lithosphere. Below the lithosphere, deeper down into the mantle, is what's called plastic-like mantle. In this case, the word plastic means flexible, not plastic like a cheap toy. So flexible mantle, and that has a fancy term called the asthenosphere. Let's look at your notes. Fill in the blanks. The asthenosphere is a thick syrup-like liquid area in the mantle. Instead of syrup, I would prefer the idea of Play-Doh. To me, Play-Doh holds its shape better. Syrup doesn't really hold its shape, and these rocks in the mantle would hold their shape until you press on them. But some people call it syrup-like, and we'll go along with that. In the asthenosphere, the liquid moves by convection currents. Hot material rises, and cold material sinks in a circular pattern. Convection currents are a cycle in which melted rock is heated unevenly. The warmer magma rises because it is less dense. It becomes cooler and more dense as it rises, and then it sinks back down into the mantle, where it's warmed again, and the whole cycle repeats. Scientists have shown that the land masses are not fixed. They slowly move across the globe. This movement creates mountains, trenches, ridges, valleys, volcanoes, earthquakes, and tsunamis. It all depends upon how the land masses collide or spread apart from each other due to these movements. I'm going to move the camera up a little bit. The main idea that we're talking about here is called continental drift. In 1912, Alfred Wegener presented a hypothesis that said that 300 million years ago, all of the continents were connected in a large supercontinent. He called this supercontinent Pangaea, which means all lands. Pan is a prefix meaning all, and then Gaea referring to land. About 180 million years ago, according to Wegener, Pangaea started to break apart, and over time the continents moved to their present-day location. The continents are still moving today. I do want to mention that these dates of 300 million and 800 million are based on naturalistic assumptions. Assumptions that scientists make as they look around the world today. They are not provable, but they are a reasonable assumption. It is up to you whether you accept these assumptions that they base these dates on or not. Some people do not accept these assumptions, and so they come up with different amounts of years ago that these actions occurred. That is up to you. So, where is the data that supports this idea of continental drift? The idea that these continents are not fixed in place but gradually move around the world. The first idea, idea number one, is the fit of the continents. The coastlines of some of the continents look as though they were once joined. The most obvious is the east coast of South America and the west coast of Africa. The second idea that suggests continental drift is fossil evidence. How do these fossils support the theory? Well, these organisms, whether they are plants or animals, could not have traveled across the oceans because either the vast distance or because the oceans are salty and would not supply the necessary environment that the animals need. For instance, if they are freshwater fish, they would not be able to go across the salty oceans. I'm going to bring the camera down a little bit closer so you can see these words better. Okay, one of these evidences is the fossil of a reptile called Cynoganthus. It is found in Africa and South America, not anywhere else. So that suggests that Africa and South America were once together. Okay, here's fossils of a freshwater reptile called Mesosaurus, found in Africa and South America. Fossils of a reptile called Lystrosaurus, which is found in Africa, India, and Antarctica. Letter D. Fossils of a plant called Glossopteris, found in Africa, South America, Australia, India, and Antarctica. How do these fossils support the theory? Well, these organisms could not have traveled across the oceans, mostly because of the salty environment there. The third type of evidence, besides fossils and the shape of the continents, is rocks. Mountain belts that end on one coastline oftentimes start again on another continent. That suggests that these belts then were continuous and that the continents were once together. The rock types, layers, and folds match across the continents. For example, the Appalachian Mountains in the eastern United States start again in Greenland and northern Europe. The fourth evidence of continental drift are climatic evidences. For instance, glacial deposits in southern Africa, South America, India, Australia, and Antarctica are very similar. Today, most of these areas are way too warm for glaciers. Letter B. Tropical swamp remains located in North America, Europe, Asia, and Southern America. These remains formed coal that is found in most of these locations today. With this data, Pangaea would have looked like this. So all the evidence that we have points towards this. The dates, once again, for how long ago this happened are based on some assumptions that you either may or may not accept. Wagner's idea was not accepted by the scientists of his day, nor during his entire lifetime, because Wagner had no explanation for how this giant supercontinent called Pangaea broke apart and how the continents continued to move. People scoffed at him, saying, what could force a continent to move across the solid ground, the solid dirt underneath it? They didn't realize that the mantle was flexible rock. They just imagined that it was solid. The making of a theory. With advances in technology, scientists gathered new data. Number 5. Seafloor spreading was another part of evidence, in addition to the other 4 that we've had. Technology that let scientists measure changes in Earth's magnetic field map the topography of the ocean floor, and they calculate the age of oceanic rocks. This supported the idea of continents and ocean floors were moving. Seafloor spreading showed that as magma pushed upwards, it caused the area around it to divide or spread apart. When the magnetic field of the ocean crust was mapped out, the scientists found the youngest rocks were near the center of the Atlantic Ocean and the oldest rocks closer to the continents. By looking at the magnetic minerals in the ocean crust, they also discovered alternating bands of magnetic field being orientated north and south. So here is the ocean crust, and this is the mantle down here. And as the convection currents bring hot mantle up, it pushes the oceanic crust upwards, and so it rises up like that into sort of like a mountain range. And then the mantle convection currents move off to the side, which drags the plate away. And as the plates separate, some of the material from the mantle comes up and cools and forms more basalt right here and creates more oceanic plates. And so the plates are spreading and growing as time goes on. And scientists, using their assumptions, will use radiometric dating to find out how old the rock is here, compared to here, compared to here. And according to their techniques, the older rocks are off away from the ridges, and the younger rocks are closer to the ridges. And from those techniques, they make a really good guess as to how long this has been spreading. They being scientists studying the ocean and the Earth's structure and all that, they sometimes blend old and new ideas into new theories. In 1960, Wegener's idea of continental drift and all this newer data of seafloor spreading were combined to form something they called the theory of plate tectonics. The theory of plate tectonics states that the lithosphere is broken into sections. Each section is called a plate. The plates can be made up of continental crust and or oceanic crust. Usually it's either just one or the other, but sometimes it's a combination. The whole plate moves together. Since plates move as a unit, major interactions between the plates occur along their margins. From the collisions, separations, and slidings of these plates, many of the different features of the Earth's surface are created. How do these plates move? The Earth's lithosphere, the crust and the rigid upper mantle, is broken into about 12 plates, 12 major plates at least. There are many smaller ones. Currently, geologists believe that the plates are pushed or pulled from below by convection currents in the mantle. The exact method that this happens has a little bit of debate to it. It's not firmly established. The scientists also believe that the Earth's gravity has some effect. And that's the end of these notes.